big data applications. When I type big data applications in the search box of google.com, these are the suggested queries returned by Google. And from this, you can see that there are indeed many different applications of big data in different areas. And as I mentioned before, this reflects the value of big data. So I will give a brief introduction of several of these applications, and hopefully you could also sense the other V's in these applications. Here's an example of big data in retail. As the figure shows here, you would have data from retailer, from supplier, from market, from shopper or customer. And you have all this data, you transform them, you integrate them together, and then you could have a scalable data or a high volume of data for you to do analysis. Okay, you can do demand-based forecasts and analytics for both retailer and supplier. For example, for retailer, you could analyze if something has some good has low sales volume. Then from the data, you could see if this low sales volume comes from low demand or comes from high price. You can do this by comparing, for example, the data of this good with the data of the other products that has the same type. Okay. Also, you could see your stock or the on-shelf availability to see whether it is comes from the low demand or the high price. Okay. Also, for retailer, you could use big data to improve the shopping experience of customers. You can do this for both online and in-store shopping based on the data collected to reflect the customer's behavior. Also, the customer's demand. You could be able to know what they like or dislike, and you can then predict the trend based on the data from previous years or from data from other states or other shops. For supplier, you could use this data to adjust the supply chain or the socket range in order to help you increase your revenue. And here is an example of big data in entertainment or media. So with the larger volume of data, you could be able to predict the audience interests because big data in the media and the entertainment industry can help in seeking an in-depth understanding of consumers' behavior and preferences. Big data could also help you to understand the customer's churn, like why subscribers unsubscribe to your mailing list. This is a $1 million question, right? And it has always seemed impossible to answer. But based on the reviews and the social media data and collecting customers' reacting and behavior, it could help you to figure out why, or at least possible reasons. Also, big data could suggest related videos. Here, it's more like a recommendation system where you have data from a historical log and have data from other customers with similar taste, their log, so you can recommend the related videos or recommended videos to the customer. Also, it helps you with the advertisement target. So big data helps advertiser and companies to better understand what kind of advertisements customers are willing to see. It also provides information about the type of content that the viewers watch at what time or what duration, so that could help you to improve your strategy of advertisement. And big data in national security. For example, Facebook has already used machine learning algorithms to detect and remove terrorist content and messaging. And if you still remember, during the Brexit campaign and Donald Trump's election as United States president, shows that how big data profiling and algorithms and using machine learning algorithms to generate news that can influence public sentiment. Well, big data could help to integrate shared information from different resources with different types and integrate them into a searchable feed, where you can see from episodes or movies that how police officers use a database to obtain information of criminals. So that is how big data could help to offer comprehensive information of the criminals. And entity recognition and tracking. For text, a good text analytics program with a machine learning algorithm can read tons of transcripts and documents in real time and identify which parts of text are relevant, which part of text are irrelevant to an ongoing investigation. Also for videos, using computer vision and video analytics techniques, we can provide similar summarizing capabilities for the hours of footage and footage and CCTV feeds to track an identified entity from camera to camera. And apparently this would help us to identify the potential risks and help us to tracking down the criminals. And by using monitors or surveillance cameras, social media, we can predict and prevent terrorist attacks. So these are all the examples that big data could be helpful in national security issues. And big data in science. Nowadays, machine learning techniques has already been used in many different science departments. And when you use machine learning techniques, you definitely need a large amount of accurate data. So that's how big data could be helpful. For example, in physics, the Large Hadron Collider in CERN collects 5 trillion bits of data every second. So that is hundreds of petabytes of data every year. So that is really a large volume of data that could be help or support the development of physics. For chemistry, we can extract information from patents and predict the property of compounds. In biology, for example, the UK's project alone will sequence 100,000 human genomes, producing more than 20 petabytes of data. So all this large amount of data generated, and they need to be manipulated and explored, such that they can incorporate machine learning to produce the valuable decisions or the values for the development of science. Also, the big data helps a lot in medicine domain. For example, big data in healthcare, we have 16,000 hospitals in worldwide which are collecting data on patients every day, and we have 4.9 million patients that are using remote monitoring device, which generating a large amount of data, and we have 1,000 readers per second, or let's say 86,400 readers per day comes from the patient monitoring equipments. We can use this data to help diagnostics or preventative medicine or popular health. For example, we can use data mining and analysis techniques to identify the cause of illness. And we can use this data to train the model or to improve the performance of the model in predicting the risk level and prevent diseases according to a genetic, lifestyle, or monitoring equipment. Also, we monitor big data, including social media data, to identify disease trend and make health strategies for pandemics such as COVID-19 this year. That's how big data could be helpful in healthcare. So there are many other applications, and we are not going to introduce each of them. But the idea here, or the purpose here, is to show you how much big data can do in different perspectives of our life, to help improve our life. And all this shows the value of big data. So that's all for the characteristics of big data, the applications of big data. Now let's look at the big data management, which is what we're going to study in this course. I think you always hearing people talking about big data management, big data analytics, and sometimes data science. Actually, data science this term becomes more and more popular, and I think we in USW we do have a bachelor degree of data science, if I'm correct. So what's the difference between them, right? And more importantly, what is big data management? Because that is what we're going to learn in this course. So again, just like big data, there is no very official definition of these three different terms. So what I'm going to say is based on my own understanding of this area. So basically, big data management, including obtain big data and store them, also the data cleaning and data integration, which also known as data preparation, as well as data visualization and representation. So all these tasks, they collect data and manipulating them to make them be prepared for the real applications, okay, or for the analytics. And big data analytics, including analyze data and make predictions or make decisions based on data using usually using machine learning techniques. Note that big data management and big data analytics, they are closely related. Big data management is to serve the purpose of data analytics. Therefore, there is a gray area, or in the Venn graph here is actually a green area, I guess. So basically, the intersection of big data management and big data analytics. For example, build index to support different search algorithms in big data analytics, or build a data flow for different machine learning tasks, or do the feature generation for machine learning tasks. All these tasks or jobs need to know what we are going to do in big data analytics, and then we can have corresponding strategies in big data management using different big data management tools or algorithms or methods. And finally, the data science. So I think data science contains both big data management and big data analytics, but it is more than that. And definitely, I mean, data science is not only focused on big data. So I won't spend too much time on the topic of data science. So let's go back and look at the big data management and the gray areas between management and analytics. For example, we want to find similar items in while doing analysis. Here, based on the different data types and different query types and the requirement of accuracy, we do have different kind of indexes. And it is only meaningful to build index when we know what we are need or what we're going to do in data analytics. For example, for sorted keys, we have binary search tree, but it only supports the existence query. We have B tree or B plus tree, which supports range search or nearest neighbor search or existence query as well. When the data type is two-dimensional data, we use Voronoi diagram to do nearest neighbor search. And for multiple dimension data, we have R tree to do range search and nearest neighbor search. All of these index structures supports exact queries. When things come to high dimensional query, it's much difficult than low dimensional queries, no matter what the query type is. But you can still get the idea here. So for different query types, we do have different index structures. And there are many other dimensions that helps us to decide which index are we going to use. For example, there are some indexes are disk-oriented, and some of them are memory-oriented. For example, B tree, R tree, the LSH, these are disk-oriented. On the other hand, we have binary search tree, a Voronoi diagram, PQ here. These are memory-oriented. Also, the scalability. For example, LSH and product quantization, they both support nearest neighbor search in high-dimensional space, but the scalability of LSH is better than the scalability of product quantization. And even for these approximate algorithms, the approximate index structures, some of them has a worst case guarantee and some of them does not. For example, LSH and Bluefintry and CountMin, they all have a worst case guarantee, but PQ does not. So yeah, again, just remember it is meaningful to build indexes only when we know what we need. So that is a good example to show the relationship between big data management and big data analytics. So in the rest of today's lecture, we're going to introduce a little bit more about big data acquisition, storage, and preparation. Okay, visualization, we have already talked about it in when we introduced the 7 V's, so we won't spend time on this again. And yeah, so let's start from data acquisition. So data acquisition is application oriented, which means you should know what data is relevant to your problem and what data is irrelevant, and you only obtain those data that are relevant to your problem. In the meanwhile, it is important to collect as much data as you could, because leaving out even a small amount of important data can lead to incorrect conclusions. That is so-called comprehensive. And in order to do data acquisition, you need to handle data from different sources with different types. These two are the variety of big data. And you also need to handle data with different velocities. Okay. So we have data from different sources with different types. And we have different technologies to do the data acquisition. For example, we have data in relational database systems. These data are structured, as they are usually tables, so we can access this data by SQL, which is what you have learned in COMP 9311, I guess. Yeah. For data in text files and Excel spreadsheets, these data are unstructured or structured data. So you access them by some scripting languages such as Python or Perl. For data from websites, they are usually semi-structured or unstructured. For semi-structured data like XML files, and for unstructured data like images or videos. And here XML is a data structure that uses makeup symbols or tabs to describe the contents on a web page. In order to access this data, you can use WebSocket services, where many websites host web services or APIs which produce program access to their data. And you can use REST, which stands for representational state transfer. It has good scalability and maintainability, and it is easy to use. That makes it popular. Or you can also use a crawler to collect data as well. Also, you have scientific data like we have mentioned before, from either physics experiments or genome data. These data either could be structured or semi-structured or even unstructured. And you access this data usually by special design softwares. This is for scientific data. And graph data. Graph data becomes more and more popular with the development of both big data and internet or social medias. So for example, knowledge graphs and social networks, these are all graph data. A knowledge graph is an ontology to represent knowledges. So basically the vertex in the graph represents two entities, and the edge of in the graph represents the relation between two entities. For example, you have A was born in location B. And you could have A is studied in C. In the meanwhile, D was born in B as well. So this formulates a knowledge graph. Okay, this is just a small example to show it. Social networks. We can use a graph structure to represent follower-followee relationship. where the node is entities and or the users, and the edge is the links between the users. So if we want to obtain data from graphs, we need to access them by special designed programs, and also the graph data is difficult to handle. For example, it's mainly because the time and space complexity of some basic operations in graph data is quite high, and the scalability of these algorithms is not very well. For example, the graph isomorphism problem is an important problem in graph data processing, but hard to solve. In real applications, we usually need to acquire data from multiple resources. So we need a hybrid of all the techniques we have mentioned before. For example, the COVID-19 map from Johns Hopkins University, their data comes from WHO, DCD, or European Center of Disease Prevention and Control. Here, the data is usually structured data, which are tables, and the data comes from media reports and social media, such like DXY, which is one of the world's last online communities for healthcare professionals, and the data comes from comes from media and social media. They are usually unstructured text data. So basically, this project needs to acquire data from website, but with different types, and then they need to extract the information from text and tables to form the map to gain this data and do the visualization. So by doing this, it actually uses different technologies for different types of data. So that is the common status of data acquisition in real applications. So after you acquired data, it is important to store them properly. So big data storage is challenging because, first of all, the data volumes are massive. So this is not only brings the pressure for disks. I mean, the reliability of storing petabytes of data is also challenging. There are many kinds of failures, either from disk or from other hardwares or from network. And apparently the probability of failures simply increases with the number of machines. But data storage is so important because you don't want to find a needle in your big data haystack. The traditional way of data storage is, for example, using relational database system managed systems. There are a couple of problems that makes it infeasible for big data. First of all, it is designed for structured data, but in big data area, most data are unstructured. And also the DBMS is designed for is disk oriented, which assume that most data are stored in disk. So this will bring a speed issue, a speed problem, especially when the volume of data is huge. So in big data area, we have some new technologies to deal with this storage problem. For example, in a relational database management system, we have SAP HANA, which is a column-oriented DBMS. HANA can keep volumes of up to petabytes of data in memory while returning query results in under a second. So it is quite impressive. However, the RAM is still much more expensive than disk space, so the scale out is only feasible for certain time critical and use cases. But still, SAP HANA offers a way to deal with petabytes of data within memory that distinguish it from traditional DBMS. Okay, we also have NoSQL. NoSQL actually stands for not only SQL. So this storage system are increasingly used to manage a variety of data types in big data. NoSQL do not represent data in a table format with columns and rows as in traditional relational databases. The examples of these data stores include MongoDB, HBase, and Hive. We will briefly introduce them in this course. And also the distributed file system, HDFS. HDFS is a distributed, scalable, and portable file system for Hadoop framework. It stores large files, typically in the range of gigabytes or even terabytes, across multiple machines. So the reliability is achieved by replicating the data across multiple hosts, and hence theoretically it does not require the RAID storage on hosts as traditional databases. I think you have learned RAID in database systems. It stands for a redundant array of independent disks. If you're not, you just Google it. Yeah. So that's for the data storage, and now let's look at the next step, which is data preparation. Here are two interesting figures. When asked data scientists like what they spent the most time to do, 60% time is spending on cleaning and organizing data, and 19% is on collecting data sets. So data acquisition and data preparation actually takes 80% of time. And when asked about the least enjoyable part of data science, more than half votes for cleaning and organizing data. Alright, so that actually shows that the data preparation is important and boring and time consuming in data science or in big data management. So here we introduce data preparation as a two-step process. The first step is data exploration, where you need to understand your data, the characteristics of your data, and sometimes you use visualization techniques to help you. The second step is data pre-processing, which including data cleaning in order to cope with veracity issue, and data integration, which is to cope with variety issue. Okay. So data exploration is the first step when you get your data. it is important for you to use your data effectively. So there are some characteristics of data that you're going to explore. For example, the trends. The trends of data shows if there is a consistent direction in which the values are moving towards. The correlations of data is the dependencies between different variables in the data. The outliers. The outliers is a data point that is distant from other data points. It could come from errors, or even it is not error, it could affect the result of downstreaming applications. For example, a machine learning task. For example, if we want to do a regression and here is the data points, then the regression would be like this. But if we have an outlier here, then the regression would be like, this. So this is how outliers could affect the downstreaming applications, or lead you to some, or at least, identify this kind of outliers could at least lead you to some special cases. So it did help you to understand the data. And there are also some statistics of data that could be helpful. For example, the mean and median are measures of the location of a set of values. The mode is the value that occurs most frequently in your data set. And standard deviation or range is the maximum and minimal number or value, in your data. This statistics helps you to identify hidden problems in your data. For example, if your data is height of individuals, and you have numbers like this, and suddenly you have a number of 1.65, then you could identify this and mark it as a dirty data, where apparently these are for centimeters and these are for meters. Visualization is an effective and efficient way to help you on exploring data. Here is also a good example of dashboard and how to use a proper way to present data as well. This is the COVID-19 map from Johns Hopkins University. Here the histograms can show the distribution of the data or the skewness or some unusual dispersion. For example, you can see the trend here, the number of new cases increased at this time point. Okay, tables can show the rank of data with exact numbers. And this bubble map or heat maps combines data with geometric information to help you on data exploration. After data exploration, the next step is data cleaning. Data cleaning is to deal with those dirty data Well, dirty data could be a mix of values or records. For example, some fields in the table are empty, and invalid data, like invalid postcode. For example, it should be 4 digits in Australia, but somehow you write a 9 digits number. It is invalid data. The inconsistency, for example, I moved from Kingsford to Kensington. The address changes, which cause inconsistency of my address in different data sources. Duplicate means 2 records refer to the same person or entity. This is when, for example, I've registered a account in some website, and I forgot about that and do it again. So I basically have 2 accounts, but they are referring to the same person. So this is duplicate. Outliers, we have mentioned it several times. So yeah, these are all dirty data. So it is impossible to prevent data quality problems because of the veracity in big data. So in order to do data cleaning, it requires you to understand data and requires you to have certain domain knowledges. And for different data types, we do have different strategies to deal with it. For example, for missing value, we could remove the records. For invalid data, we usually estimate for a reasonable value that can be used as a replacement. This is also can be used to for missing values as well. For example, if we want to know age value of a employee, either it is missing or it is invalid, a reasonable value can be estimated based on the employee's length of employment. The inconsistency, we could do some additional work to resolve the conflict. For example, we use mean of the 2 conflicting records, or the maximum or the minimum, depends on the case, right? For duplicate cases, we can merge them together. For outliers, we usually just remove it. The domain knowledge is essential when you're making decisions on how to handle incomplete or incorrect data. So yeah, domain knowledge and the understanding of data is quite important to data cleaning. Data integration is the next step after data cleaning. So basically, the data integration means you merge data from multiple complex and heterogeneous resources. The goal is to perform or offer a unified view of data. Data integration is a mutual field in traditional databases. The traditional way of solving this problem, including schema mapping, record linkage, and data fusion. We have mentioned about schema mapping when we introduced the variety of big data. So yeah, we have also mentioned the difficulty of schema mapping in big data. For record linkage, the task is to identify whether two records refer to same entity or not. But in big data, the variety and the velocity properties actually increase the difficulty of record linkage task. For data fusion, the task is to resolving conflicts. The difficulty or challenge mainly comes from veracity of big data. So there could be more conflicts or uncertainty, then it is harder for you to resolving the conflicts. So basically, data integration in big data remains an open problem because these new challenges brought by the properties of these V's. So these are the major steps in data management, and I would like to spend a little bit more time on data creation, where many students asked questions about this issue, and as well as that figure about data variety and data creation. So data creation, just like big data, again, it does not have a very standard definition, but let's quote this from Professor Renee Miller. Data creation includes all the processes needed for principled and controlled data creation, maintenance, and management, together with the capacity of adding values to data. So let's acknowledge it to an art curator. An art curator is responsible for the acquisition and care of works of art. So he or she may make decisions regarding what objects to collect. In data creation, we need to make decisions regarding to what data to collect. A curator oversees their care and the documentation of these works of art, where data creation oversees data care and documentation. A curator conducts research based on the collection and provide proper packaging of art for transport. Here, we conduct research based on the collection of data, and we do data-driven decision-making, and we also ensure proper packaging of data for reuse. And finally, a curator shares that research with the public and scholarly community through exhibitions and publications, where data creation share that data with the public. So basically, the data creation is just like a curator, but the objective of curation is not works of art, is data instead. So I would like to say that data creation basically includes the data the data acquisition and data preparation processing that we have introduced before, but they do have slightly different focuses. Now let's come back and look at this figure again. So this figure basically shows three things: the characteristics of variety, the benefit of variety, and the challenge of variety of big data. So the x-axis is the number of data sources, and the top part here is the how things changes with the number of data sources. For example, when the number of data sources is low, is small, sorry, the data format is usually relational or tabular, and the data generation is centralized, and the data source usually from consistent schemas or solid databases. And when the number of data sources becomes large, the data is decentralized, unstructured, and the data sources usually are information extraction or unstructured data. Yeah, so this is number is small, and this stands for large, large number. All right. And the data consumption cost increases with the number of data sources, as it is possible to gain more from more data, especially data from different sources. The long tail allows data consumer to have a more comprehensive model of their domain that can be searched or queried. And how data curation can help here is to reduce this line to this line here. It reduces the consumption cost, hence improves the scalability. So this is the benefit of data variety. The challenging of data variety is that how to deal with data from multiple sources with multiple format, especially when do curation. So that's basically what does this figure try to illustrate. So in this week, we have introduced this course. We have introduced the big data management, including 7 V's in big data, the applications of big data, and the core steps in big data management. So from next week, we will discuss the techniques in big data management, start from Hadoop and MapReduce. That's all for today, and thank you for watching.